Alrighty boys, it is finally time for the long-awaited physics content. What the heck? It's crazy. What's also crazy is that I have not done physics in eons. God dang it. Bruh. So this should be fun. I have no idea how this is gonna go. Of course, I've already taken these before, so like last year. I hopefully don't remember the questions too well, so this is probably gonna be helpful for you guys, but I don't know if I know any physics anymore. This is so sad. Hello everybody, I'm Karar, and today we are going to be doing a live solve of the EFMA 2028 exam. But dude, EFMA does not have the EFMA 2020 exams without the solution, so it's kind of triggering. Luckily, I got this boy. So just quick shout out to Weird Flux, but okay, he's the guy who like cleared out the answers for me so I could take the test in an actual live solve situation. So big thanks to him. Check him out. I'll put his channel link in the description. But let us get started with the problem solving. Okay. 75 minutes on the clock. Alright, probably have made this first. Alrighty, okay. A ball is launched straight towards the ground from a height h, right? So it's gone this way, okay. When it bounces off the ground, it loses half of its kinetic energy. It reaches a maximum height of 2h before falling back to the ground again. Okay, so essentially we know that like 1/2 mv squared plus mgh is the original energy of the ball, right? And basically, when it reaches the ground, all of its potential energy is converted to kinetic energy, right? So essentially, if it loses half of its kinetic energy, its overall energy is going to decrease by 1/2, right? So essentially, its final energy is going to be equal to this, but that is also equal to mg times 2h. Oh, that is not a 2. What the heck is that? Bro, 2h. So if we just solve for v, we should get our answer. So we get 1/4 mv squared is equal to 3/4 mgh. Or sorry, 3/2 mgh. So if we just do this, we get v is equal to √6gh. Okay, so that is E. Alright, number 2. A rigid ball of radius r is rolling without slipping along the rib of a right angle chute. Which of the points of the ball will have maximum speed? Okay, so essentially the idea is you have, well, you basically have this, right? Hold up. Right, and you basically have it rotating around this axis, right? So essentially, the angular speed of stuff around this point is the same for all of the stuff. So angular speed is the same. So essentially, the top point is going to have the most like horizontal velocity, and then obviously the center of the ball is also moving. So this has even more, right? So yeah, because basically these points are effectively stationary for like an instantaneous amount of time, right? So this guy is the guy who has the largest distance, so your velocity is equal to omega r, so the highest point should have the largest speed. Okay, so that is E. Okay, E again, really? When an axe is swung with kinetic energy E directly at a piece of wood, the edge of the axe is buried a depth L into the wood. Okay, if the axe is swung with kinetic energy 2E, how deep will it be buried into the wood? Assume that the axe is wedge-shaped with a constant angle, and that the force per unit area contact area between the axe and the wood during impact is proportional to the depth. Okay, so we basically have this, the force per unit contact area. So basically the pressure, right? Okay, so let's just say the current depth is like x, right? Then the force per unit area, how does the area increase with depth? Well, basically, as you increase depth, it's like a similar triangle, right? So basically your contact area is also going to increase the same, proportional to x, okay? So contact area is proportional to x, A is proportional to x. So that means the overall force is proportional to x squared, right? So essentially you have a force this way that is proportional to x squared, and essentially your kinetic energy is equal to the work done like in the opposite direction, right? So essentially if we integrate the force over the distance, right? Or sorry, it'll be like integral of x squared from 0 to L, right? So that's essentially just like L cubed, right? So it's proportional to L cubed. So essentially energy is proportional to L cubed. Okay. Alright, so basically if energy is proportional to L cubed, then we basically have, if we multiply E by 2, then we need the L to be multiplied by cube root of 2, so that should just be B. Very nice. Alright, number 4. 4 identical rods, each of mass m and length 2d, are joined together to form a square. It is then spun around a circle or center, as shown in the figure, at an angular frequency of w. What is the magnitude of the force that the joints between the rods must bear? So I'm assuming there's some tension, right? Really? Wait, how does this work? Okay, so the rods want to move outward, right? So essentially, each of the corners has to exert a force on each of the rods to keep them from going outward, right? Okay, so there's one moving this way, one moving that. Yeah, so okay, basically the idea is you have these things, right? And you have the center, and all these things want to move away from the center, right? Like it's like centrifugal force, right? I mean that's obviously a fictitious force, but it still is important, right? So essentially we could find the like centripetal force that needs to be accelerated or needs to be exerted on each thing, right? And essentially, yeah, so the force that needs to be that needs to be exerted on this guy and this guy. Okay, okay. So basically, the force needed to be exerted on this guy is going to be distributed between these two, right? So essentially, we add up like half of this force and half of this force, and we're good, right? But we had to add it like vector add, right? Because essentially, you're basically adding this vector plus this vector, and you get something like that. So the joints that are going to go this way, right? All right. So first off, let us find the centripetal acceleration, right? So we basically have that is v squared over r is centripetal acceleration, which is also the same as, is it r squared w? No, omega squared r, right? Yep, and then it should be m. Okay. And why does the length matter? Oh, yeah, r. Okay. So if these are 2D, right? So this is d, then the r is going to be, or no, r is going to be this. So r is d, okay? Because we're only doing the center of mass, right? Okay, so this is the force that needs to be applied to each rod, okay? So then we divide by 2 to get how much is this way for this joint, and then we had to add in another thing, so multiply by root 2. So divide by 2, multiply by root 2, and it's basically going to be b, right? M omega squared d over root 2. So that is b, okay. Okay, number 5. A pendulum with length L oscillates inside a box. The person picks up the box and gently shakes it with frequency omega. The final amplitude can be maximized. Oh, I hate these. God dang, I forgot how to do these kind of things. Okay. So I think it's kind of like the idea with the swing, right? Like if you push it when it's at its, bottom? Or at its top, what's better? Yeah, I think if you push it at the bottom, right, then, wait. Huh. Okay, basically when it's moving up, you want to decrease gravity, right? And then once it's moving down, you want to increase gravity, right? Yeah, so basically whenever it moves up, you want to, wait, okay. So whenever it moves up, you want to be moving the box down. And whenever it's moving down, you want to move the box up. Okay. So how often does it translate between moving up and down? So one period is going like this, like that, right? Okay, that's one period. But it flips every fourth of a period, right? So every fourth of this period, it flips. Okay. So essentially we need 1/4 of the frequency. Wait, no. Need 4 times the frequency. Okay, need 4 times the frequency. Alright, that makes sense. So essentially the angular frequency of a pendulum is root g over L, right? So essentially if we want, wait, what? It's like, no, it is root g over L, so it's saying it'll either be 2 or 1/2 of it. So if you do it twice the frequency, right, then essentially it'll go up, you're still moving it up, then it'll go down. Well, all we know is that it should be bigger, right? So I'm assuming it should be B. Alright, so I'm just gonna go with B, because it for sure should be bigger than the actual thing. Okay, a planet is orbiting a star in circular orbit of radius r0 over a very long period of time, much greater than the period of the orbit. The star slowly and steadily loses 1% of its mass. Throughout the process, the planet's orbit remains approximately circular. The final orbit radius is closest to, okay. What's the law for this? Let's see. So what's conserved? Is angular momentum conserved or something else conserved? Well, okay, so first off, if you have like this, right? Like that, and the m is decreasing, right? Okay, the planet's orbit remains approximately circular. Well, okay, we logic this out, right? If it loses a tiny bit of its mass, right, then the force on this guy is going to be a little bit less, so it'll move farther and farther away, right? That would make sense. I'm just not sure what the conservation, which conservation principle is applied here. Let's see. Okay, let's just think about it, right? So if in a circular orbit, you basically have gm little m over r squared is equal to, so that's the force, is equal to mv squared over r, right? So essentially, g big M over r is equal to v squared, right? But the velocity might change too, so that is annoying. Okay, let's think if angular momentum is conserved, right? So angular momentum is only not conserved if there is an external torque, right? So there is no torque, so I'm assuming that that is a thing. Okay, so you have this, and you also have that mvr m1 v1 r1 is equal to m2 v2 r2. Or well, I guess it's the same, so that's fine. Okay, but we also know that v1 r1 or v1 squared, from this we know that v1 squared r1 is equal to 0.99, or this time 0.99 is equal to v2 squared r2. Okay, so essentially if we divide this over here, then essentially we just got r2 is equal to 0.99 r1. Does that make sense? Because I'm pretty sure angular momentum should be conserved because you're not like losing any torque. There's no torque on the like external object, right? Because it's always going to be perpendicular to the orbit if it always stays circular, right? And then that should also be true because it's a circular orbit, so seems legit. Alright, so we're gonna go with D. Or speed up. Yeah, something like that. Okay. Alright, 7. An astronaut standing on the exterior of the International Space Station wants to dispose of 3 pieces of trash. They face the station's direction of travel with the Earth to their left, okay? From the astronaut's perspective, the 3 pieces are thrown left, right, and up, okay? So some of the pieces return to the space station, okay? So essentially you have your Earth and you have your space station moving very, very fast, okay? Now, I think I remember this one because it's kind of hard to forget, like, conceptual questions, and everybody trolled on this one, so I think I know it, although I don't remember looking at the answer key, so maybe my friends were trolling me. Okay, so basically what I heard is like, if you throw it to the left, right, your throw speed is like nothing compared to the speed of your satellite, right? So essentially, your thing is literally just gonna go all the way around the Earth and come back right there. Well, okay, so essentially they're facing this way, and then okay, so they're facing this way, Earth is to the left, so this would be left, that would be right, and that would be up, right? I feel like the one that you throw up is like this way, so coming out of the page towards me. So like the one you throw left will go a little bit like that, but it'll basically be the same as your satellite orbit, so it should eventually come. And then if you throw it up, then it's like literally the same as your satellite orbit, right? Well, I mean, it's basically the same concept. I'm just gonna go with 1, 2, 3 because basically your throw is irrelevant compared to the satellite speed, right? So essentially it should like follow a similar orbit to your satellite and eventually come back. So should be E. Alright, 8. The velocity versus position plot of a particle is shown below. Which of the following choices correctly plot acceleration versus position? Okay, so essentially, versus position though. Oh, okay, well that's annoying. Alright, let's see. So, let us think. So essentially, it's velocity at position. Okay, so v is equal to like kx, alright. So essentially, your dx over dt is equal to kx, right? So now essentially we want to find acceleration. So if we take the derivative of both sides, you basically have that your acceleration is equal to kv, right? Which is equal to kx, so it's k squared x. I feel like that should work, but let us just make sure. So essentially we could solve for x, so dx over dx dt k is equal to, okay. So essentially we have ln of x plus c is equal to kt. Basically says e to the kt is equal to k, or like some other constant c is equal to kt is equal to x, right? Yeah, which basically means that everything's going to be proportional to x, so it should just be a straight line. Yeah, it should be a straight line, so C is the answer. Alright, 9. So a block of mass m is attached to a massive string. The string is passed over a massive pulley, and the end is fixed in place, okay? The horizontal part has length L, and then essentially you hang something here. The tension at the end of the string, okay. Okay, for that equilibrium, like the tension always has to be like mg, right? Like the only way in order for this to work is if the tension in the string at the end right here. Wait, which end though? Oh wait, this is the end. Wait, okay, no, no. So tension in the spring is the same everywhere. Okay. Yeah, okay. So tension in the spring has to be mg, otherwise this guy would be moving. So our answer is literally just, uh, yeah, it should just be B, unless I'm trolling, which is very possible. Okay, number 10. And during the process, the block, so the bottom block, has been raised by approximately a height. Okay. So, first off, to get this to equilibrium, right, you basically need this force to be mg, right? But you basically have tension here, tension there, and we know that T is equal to mg, right? So essentially we need the upward component of each of these T's to be 1/2 of T. Okay, so essentially in order for that to happen, we know this has to be a 60-degree angle, right? Because cosine of 60 degrees is 1/2, so we know that. Okay, so essentially it was initially L, right? But now we're taking up like L over root 3, or L root 3, right? L over 2 root 3, okay? L over 2 root 3. And essentially, our new length minus our old length is the amount we lifted up, right? So essentially, it's just going to be L root 3 minus L. So if we do that in the calculator, it should just be root 3 minus 1. Root 3 minus 1 is 0.73, which is not even close to an option. Hold up. Oh, it's L over 4, because this part's L over 2, so this would be L over 4, which would make this L over... Okay, so this is L over 3 over 2. Okay, that makes a bit more sense. So now we do squirt 3 over 2 minus 1 is smaller than 1. Wait, what? What am I doing? Okay, so L over 2, L over 4, L over... Oh my god, I'm so bad at math. Okay, so this should be L, 2L over root 3. Okay, and then, so divide by root 3, multiply by 2, but then L over 2, so it should be L over root 3. Okay, so this should just be 2L over root 3 minus L. What am I doing? God dang. Alright, so you basically got 2 over square root 3 minus 1 is 0.155. Okay, there you go. Alright, hey, there you go. Why am I being so... Bro, I'm too slow at this game. Okay. 11. The maximum tension per area material can sustain without failure is called tensile strength. Plain steel has a tensile strength of 415 megapascals. What is the maximal mass one can hang on a vertical steel rod with negligible mass and a diameter of 2 centimeters? Okay, so you have this, you have that, you have 2 centimeters. Oh, that's 2 centimeters. Okay, so first off, we could basically do the force, which is like mg over area, is equal to 415 megapascals. And I forgot, are we supposed to use 9.81 or 10? I forgot how FMO works. 10, right? Yeah, 10, okay. So we essentially just do 415 times 0.01 squared times pi. Wait, it's a cylinder, right? Yeah. Over 10 times 10 to the 6, because we have mega. Seriously? 13,000 grams. Is that right? Oh. Wait, what? 13,000 grams. 10 to the 6, right? I multiplied by? Divided by 10 times 10 to the 6. So this divided by 13 kilograms. That's not right, though. For sure. Maybe I'm missing a 10 to the 3 somewhere. Am I? I'm pretty sure I'm not. God dang. Okay, we're just going to go with C, because I'm pretty sure that is right. I'll come back to it if I have time. Alright, so a point mass, M, is glued inside a massless hollow rod of length L at an unknown location, okay? And when the rod is pivoted at one end, the period of small oscillations is T, and when it's pivoted from the other end, the period of small oscillations is 2T. Okay, so basically just saying that, like, it's a pendulum, and you have some X and M. And since the rod is massless, it doesn't have moment of inertia, so essentially it is just a pendulum. So root G over L is our thing. So originally our L is 2 pi root L over G is what we get. So essentially if we had to get 4 times. So the new X, after you pivoted from the other end, should be like 4. So yeah, okay, so basically you have X and 4X, and your center is at 5X over 2, and this is at X, so you basically have 5X over 2 minus 1, which is equal to 3x over 2, and x is equal to L over 5, so we basically have 3x over 15, wait, 3x over 10, yeah, okay. 3L over 10, my bad, so that should be a D, okay. 13. A ballerina with moment of inertia, eyes quickly twirling in her hand, she has a pen of mass M at a radius r from her axis of rotation. The ballerina releases her pen afterward. What happens to the vertical component of the angular momentum of the system, consisting of the ballerina and the pen? You may ignore all friction, but not gravity or normal forces. Okay, so the only way for her angular momentum to decrease, right, is if her the vertical component is basically like you're like on the flat plane, okay? The only way for that to happen is if there's a torque, right? So does gravity and normal forces create a torque on it? No. Does friction create a torque? Yes, but like there's no friction, so there's no way to make a torque, so I'm assuming it stays the same. Why would it? Yeah, I can't. It's of the whole system, right? Yeah, it's including the pen, so nothing leaves the system. There's no torque on the system, so it has to be C. Okay. 14. All right. Two blocks of mass m are placed on top of each other, and the bottom block is placed on the ground. The ground is frictionless. The static and kinetic coefficients of friction between the two blocks are mu s and mu k. Okay. Okay. The blocks are at rest initially. When a constant horizontal force is then applied to the bottom block, which of the following graphs could show acceleration as a function of f? Okay. So the ground is frictionless. So essentially, okay, so while they move together, your acceleration is equal to f over 2m, right? But once you get past the coefficient of static friction, then your acceleration is equal to, so essentially, like, this guy is going to start moving back, so the friction force on it is going to be towards the right? So essentially, the only force on the top guy is friction, right? So on the bottom guy, you're going to have a backwards friction. Okay, so you're going to have F minus, like, mg mu k, right? Because the normal force on this dude is mg, right? And then the kinetic friction on this dude is going to be rightward mg mu k. So on the bottom block, it's going to be minus mg mu k, because opposite equal and opposite, okay? And then just divide this whole thing by m. Okay, so when does it slip, right? So it slips when the mg mu s is like less than f over 2, right? Because you need like essentially, okay, so when mg mu s is f over 2, right, then it's barely enough to keep the other one moving forward, but at the same time, yeah, so it's barely enough to keep that going, so it'll be equal to f over 2. However, mu s is less, so this part is going to be bigger than this, so our acceleration is going to dip and then go up at like a faster rate, because here the coefficient is f over 1 half f, but here it's just f, so it'll increase at twice the rate, so it should be E. Wait, really? The static friction is less? Well, that's interesting, but it should be E. Okay. 15. Alright, as shown, a vessel contains two types of liquid, the liquid with density rho 1 on top and rho 2 on the bottom. The depth of the top liquid is h1, and the interface area between the top and the bottom is s1, okay? And the bottom has h2, okay, and the area is s2. Oh, bro, I hate these ones, god dang it. Okay, I'm pretty sure, okay, so, it's asking for force or pressure? Because I'm pretty sure it doesn't impact the pressure, like, changing the areas. Okay, so, obviously, like, the pressure due to the top guy is going to be rho 1 gh1, right? And then I'm pretty sure the next one is just rho 2 gh2, and that's it. And you don't have to do anything fancy with the areas. Yeah, because basically, like, pressure is transmitted equally to everywhere in the thing. So essentially, like, increasing the area doesn't impact, like, that pressure, right? It basically, yeah, it doesn't impact the pressure, so area doesn't really matter. So I'm assuming it does this. Yeah. The only thing that will impact it is the gravity stuff. So I'm just going to go with A, alright. Liquid droplets store a given amount of potential energy per unit surface area due to their surface tension. When two identical, nearly spherical liquid droplets coalesce on a certain type of surface, part of this energy can be converted to upward kinetic energy, causing the coalesced droplet to jump. Assuming, okay, so what does the maximum height depend on the radius r? Huh. Okay, so they store per unit surface area. So radius r of the droplets, do we assume they're spherical or something? Yeah, okay, nearly spherical. So your surface area is proportional to r squared, right? Which means that your potential energy is proportional to r squared, which means that your upward kinetic energy is proportional to r squared, right? Then what is your height in terms of kinetic energy? So mgh is equal to 1/2 mv squared. So essentially your height is directly proportional to your kinetic energy. So your height is going to also be proportional to r squared. Right? Does that make sense? Oh, but mass is also proportional to r cubed, right? So mass is proportional to r cubed. Huh. Okay, so you have to divide by... Oh, okay. Huh. Alright, so essentially your PE is equal to 1/2 r cubed v squared. So v is proportional to r to the negative 1, right? And your h... Or wait, what? No, your v is proportional to r to the negative 1/2, right? And then your h is proportional to v squared. So should it be r to the negative 1 then, right? Because if you square this, you get that. Yeah, I think negative 1 seems legit. Alright, 17. Alright, Paul the Giant stands outside on a force meter calibrated in newtons, which reads 5,000 newtons. Dang, he big, alright. Paul is wearing a large cowboy hat, which has horizontal cross-section A, and completely covers both him and the scale when seen directly above. And essentially, at time t, he starts getting rain, and any rain is collected, so it just stays there. On the ground? Wait, what? How big's the ground? Oh, so that is per unit area. Okay. Okay, so essentially, yeah, 0.001 meters per second, right? So essentially the volume that lands on it is like times 1, so you have 0.001 meters cubed per second, right, on the hat. So the momentum, okay, so force is equal to momentum per unit time, right? So essentially this times the density of water, right, which is 1,000. So that gives you 1 kilogram per second, right? And then if you multiply by velocity, you'll get momentum per second. So it'll just be times 1. So this is also your times kilogram meters per second squared. This is the downward force on the guy. So it's for sure like 5,001 something, right? And then you also have to add in how much per unit time. So how much does it weigh? So we know that this is the weight of the water, right? 1 kilogram per second, right? And then you have to multiply by g, right? So it's 10 kilograms per second. So it should be b, right? Alrighty. Well, 10 newtons per second. 10 newtons per second because you're multiplying by g. Alright, seems legit. A massless rigid rod is pivoted at one end and a mass m is at the other end. Originally, the rod rotates frictionlessly around the pivot with an uniform angular velocity such that the mass m has speed v. A rotating rod collides with another mass at its midpoint, which then sticks to the rod. Okay. So essentially there's some inelastic collisions going on here. So, okay, so massless rigid rod. Okay, so original angular momentum is mvr. And essentially there's no external torques, so the angular momentum should be conserved. Okay, so this is going to be equal to mv prime r plus mv prime over 2, because the angular speed of both of these are the same, but the velocity is actually half, and r over 2, which basically says that v prime is equal to v over, so this is going to be 5/4 v prime, so 4/5 v. So because it's 4/5 v, we could basically find the kinetic energy of the system as I omega squared. So we had to divide by r. Well, yeah, so it'll just be over r. And our moment of inertia is just m r squared plus m times 1/2, or r over 2 squared, that's our I, times r omega, which is just going to be 4/5, wait, what? 4/5 v. Yeah, okay, so 4/5 v, like v is the speed of the outer guy, so that should be fine. 4/5 v over r squared. So this basically gives us, so it'll just end up with 4/5 mv squared, okay. Oh yeah, 1/2 iw squared, 1/2 iw squared. So it should give us 4/5 mv, 2/5 mv squared. Okay, seems legit. 18d. Okay, 19. A system of cylinders and plates is set up as shown below. Okay, so essentially we have like a bunch of plates, have cylinders, and I'm assuming they roll without slipping. Okay, they do. Okay, so they all roll without slipping with angular speed w. So essentially the relative speed of this point and this point have to be, so angular speed omega. So this has to be omega r left, this has to be omega r right, and then same thing for this, right? So this plate is moving 2 omega r relative to this plate, then this plate is 2 omega r relative to this, and so on and so forth, so it should just be E. Dang, why is 19 so easy? God dang it. Unless it got it wrong, which would be sad, but I'm pretty sure that's right. Okay. A car is driving against the wind at a constant speed v0 relative to the ground. The wind direction is always opposite the car's velocity, but its speed fluctuates about an average speed of v relative to the ground. The air drag force is always a v rel squared, where, okay, what are the average rate of energy dissipation due to air resistance? Okay. Okay, so basically your what? Let's see. So basically your power is like what? uh, okay, so you're going v0 this way, and then you're going v plus or minus some fluctuation. Let's just call it f. So your air drag force is just gonna be a, like, I don't know, v rel or v0 plus v plus or minus f squared. So what is the average rate of this? I mean, you for sure can't average out the f's, right? Because there's going to be an f squared somewhere, so we need to somehow know the average of the square somehow. Yeah, we don't know the average of the square of the speed. Wait, so when would squared be not same? Okay, so obviously, like, if it fluctuation just happens to be 0 the whole time, it could technically be like equal, right? Because then this would just get rid of that. Okay, so A is for sure possible. So how do you get left? All right, so basically your energy dissipation is just like integral of PdT, right? So basically your over t, right? Okay, so could an integral of v0 plus v plus or minus f squared. Okay, so basically we know that integral of v plus or minus f normal dt over t is equal to v, but that does not tell us anything about how to do this because there's a square. So it could be less. How could it be less? Okay, let's just think about it, right? So if we have like 1, 2, 3, and we want to find the average of the squares of these, so obviously the average is 2, but then the average of the squares of these is 1 plus 4 plus 9, so that gives us like, what, 13, 14. So that is clearly bigger. Wait, what? Average over 3. So 14 over 3. Well, that's greater than 2 squared, right? Okay, so that's greater than 2 squared. So technically, it could be greater, right? What about, could it be less then? Oh, well, I mean, that's the only option. So it should be, wait, what? Wait, so A is for sure true because the, wait, is it? What? Let's see. Okay, could it be less? Let's see if it could be less. So if we do like 2, 3, 4, and we do 4, 9, 16, then this will be 29 over 3. So is that bigger than 9 or smaller than 9? That's bigger than 9. So it seems like it's always bigger. But could it technically be equal? Huh, so it's either B or A. Like, does fluctuate mean that it necessarily has to fluctuate, right? Like, does a flat line count as fluctuation? Because I feel like there's no way to get exactly equal. Maybe like, okay, well, why don't we see if we get two values. So we have A and B. So A plus B over 2 is the average. And we want A squared B squared over 2 equal A plus B over 2 squared. So essentially that reduces to like what, A squared plus B squared minus 2AB over 4 or something. So A minus B is equal to 0. Okay, so technically if they're all equal, then it will be equal to that, but are you allowed to do that? Okay, I'm just going to go with B because I'm assuming fluctuates means that it's not always the same. And I'm pretty sure there's a theorem that says that it's always going to be greater than the average of not fluctuating. So I'm going to go with B. Okay. A circular table. Alright, a circular table has radius r and n greater than 2 equally spaced legs of length h. So you basically have uniform mass density with total mass m. Okay, and you can neglect the mass of the legs. Okay, so essentially there's two ways to flip this table over, right? So essentially you could tip it over like this side right here. How else could you tip it over? Is there any other way to tip it over? Like, you can't do this without like going on these legs. Okay, so I'm assuming like this is the best way to tip it over. There's no reason to tip it over like this, right? basically, in order the minimum horizontal force needed to tip over the table is going to be where it has the least what do you call, where it has the least moment of inertia, right? So essentially, you want it to be as close to the rest of the table as possible. Okay, let's see. So you have a side view of the table, right? And you have like legs. So you can either have it like this, or wait, no. So it'll be like 2 over there. Is there any other way to flip it? Like, you can't really. Okay, so essentially the only torque here is, well, we could just treat it as the center of mass. So the only downward opposing torque to our F here is going to be mg, right? So essentially, if we look at it from the top, we basically have theta, and this is like something r. Okay, so this is r. So then we want to tip it over these two legs, right? So the lever arm, right, this length here is going to be r, r what? Sine theta over 2. Well, that gives you, oh no, r cosine theta over 2, right? Which is give you this lever arm. So mg times that is equal to r fh. 22. A collision between two masses occurs, okay, in each inertial reference frame. One can compare the energy in total momentum, delta P, and the change in total kinetic energy, delta K, during the collision. Which of the following is true? Delta P and delta K do not depend on the frame. Okay. So, essentially the only thing that is, like, delta, okay, let's see. So, essentially you have, M1, okay, let's just say you have M1, M2, like V1, V2. So essentially you just have M1 V1 plus M2 V2 is equal to, like, what? Okay, isn't delta P always 0, right? Yeah, so delta P should always be 0, I'm pretty sure, no matter what. Yeah, I mean, it literally says it does not depend, but K might. Does K? Okay, so basically we just have to check if K depends on it, because I'm pretty sure in inelastic collisions, nothing changes about momentum, right? This thing is always true, and you could change, like, add a constant or not to each of these, and it'll be fine still. Okay, but then if we have kinetic energy, wait, so then shouldn't it just be C, right? Like, oh, it could also be A. So C or A, we'll have to figure out which one it is. So essentially you have 1/2. So we only care about like inelastic collisions. Wait, what? How does it not matter? Oh, okay. So let's just say mv prime squared minus 1. Okay, so mv prime 1 squared minus 1/2 m v2 prime squared, m2 v2 prime, or no, m1 v1 squared, okay, plus 1/2 m1 v2 squared prime, or m2 v2 minus 1/2 m2 v2 squared. Okay. Wait, doesn't this also depend for elastic though? Oh yeah, okay. Well, I think for inelastic is for sure. Oh, because it's 0 for. Yeah, okay. I think, yeah, okay. So I think I'm just gonna go with C, because I'm pretty sure it doesn't depend on it for elastic, but, well, I mean, it for sure does for elastic, but I'm pretty sure it doesn't for inelastic, so that should be fine. Because energy is basically not conserved, so you can't do anything. Okay, makes sense. 23, alright. How much time do we have? 10 minutes, god dang it. Alright, so he determines the spring constant K by applying a force to it and measuring the change in length. And they both have constant uncertainty, okay. So then K is equal to F over delta X, right? So essentially your, the formula is your uncertainty of K is equal to your root of, or over K, value of K is equal to, what? Of F over F squared plus of X over X squared. Okay, so originally this, like, times K gives you that. So if you multiply the force by 5, your K also gets multiplied by 5, so you get 5K root your same tool, so this stays the same, over 5F squared plus, oh, they both have the same absolute uncertainty. Okay, so this would also be like F, so this is F over X squared. Okay, wait, how do you multiply this to get there though? Oh no, this is different, so this is X, okay. Oh, the same spring constant. Oh, so that means this is also 5x. Oh, that makes so much more sense. Okay, so essentially it's just the same, right? Wait, what? Okay, so this is 5 squared Oh, so this is the same. Okay. Oh, okay. So 1/5 of it. All right, that makes sense. That makes sense. Okay, so this is the equation. You basically get over 5. Pull that out, and you get 0.2. Okay. Nice. So answer is C. 24. A mass M is connected to one end of a zero-length spring with a spring constant K. The other end of the mass is connected to a frictionless bearing mounted on a horizontal pole. Okay, so that the mass can swing in a vertical circle of radius r. Okay, well, the vertical distance between the center of the circular orbit and the axis of the pole. Okay, I just remember that I had no idea how to do this during the actual thing, and I did not get it right. So hopefully we can do something different this time. Let's see. So maybe we could put this and then put a spring out of here. Okay, so then the force is always this way. So how do you keep that in a circle then? Oh, but not a constant speed circle, which is annoying. All right. But then there's also gravity, which is also annoying. So, Oh, so you could basically, so the rest length is negligible. So essentially, you could consider this to be kr, right? Maybe we could like find the bottom and the top. Oh, maybe we find the bottom and the top of the thing. Then that would help. I mean, how did that help exactly? So, okay, at the bottom, you basically have h plus r, let's say. So essentially, you have k times, how much time do we have? Okay, let's just see how far we could get. So k plus h plus r is equal, or minus mg is equal to mv squared over r. Okay. Okay, also the spring never does any work on the block, right? So essentially only mg is going to change the speed of the block, right? Yeah, so only mg can change the speed of the block, right? Oh, but it could, because it's not necessarily perpendicular to the path anymore because it's not the center. Bruh. Okay, where else is stuff being stored, like potential energy though? I'm pretty sure it's just in the spring. So essentially, your potential energy at the top is like r minus h squared plus what mg times 2r plus 1/2 mv squared is equal to the bottom mv squared 1/2 mv0 squared plus 1/2 k times r plus r squared h squared. Okay. So essentially, this becomes mg or 2mgr is equal or plus 1/2 mv squared is equal to k times h plus r minus mg whole thing times r over 2 plus krh. Okay, or 2krh. This seems very nasty though. Okay, yeah, I'm probably not gonna get this in the time, so let us move on. A ball with a radius and mass m is connected to two ideal springs. Okay, each spring has rest length L0. The springs are connected to the ball inside a box of height length 2L, and the ball is allowed to come to equilibrium as shown. Under what condition is the equilibrium point stable with respect to small horizontal displacements? Okay. Okay, so you basically have this, right? And this upper thing is pushing down on it, right? Or no, pulling up on it. And I'm assuming this guy's also pushing up on it. And then downward is mg. Okay, what should we guess for this one? Let's say B, why not? I don't know, why not? Okay, then 25. Let's see. I don't think I can get it in the time. Bro, my time management skills have gotten so bad now. That's so sad. Okay, let's see. So essentially, if it moves to the right, then your bottom guy is going to be pushing with K2 a little bit more less. Yeah, it's going to be pushing a little bit less upward, and then this guy is going to be pulling a little bit more. Yeah, this guy's going to be pulling a bit more. Yeah, I don't know. Okay, let's just guess C. Why not? C. Okay, let's bruh. I will try them after we check our answers. I am not going to pretend that I did it in the time. Let's just check our... Actually, wait, we have 1 minute, 15 seconds left. Let's just make sure we did this one question that we trolled on right. Okay, so you have 415 megapascal. Mega is 10 to the 6, right? I'm not trolling. Okay, what is the Maxwell mass that can hang on a vertical steel rod of negligible mass and a diameter of 0.2. So your radius is 0.01, okay? And it wants the mass, right? So divide by 10 and you get gram. Oh, bro, I'm so stupid, dude. I literally thought that gram was the SI unit of mass. What do I do? Okay, we're chilling. Okay, I think our time is up. Let us check our answers. Bro, why did I think gram was the SI unit of mass? Okay. Alright, let us check our answers. 2020 FMA answers. Alright, so E is correct, E is correct, B is correct, B is correct. A, really? Oh, we shake it horizontally, dude, I'm so stupid. Bruh, I thought he said vertically. What am I doing? Oh, god dang it. Alright, so basically the reason why it's, if it's horizontal, right, then like, basically the reasoning is because like if it's horizontal, right, when it's moving this way, you want to move the block the other way, right? So that essentially accelerates it this way, right? So when it's moving right, you want to move it left, and when it's moving left, you want to move it right, your box. But isn't, okay, so it moves right, but doesn't it move right for half of its, period? Oh, period, okay, so, oh, okay. So the force's frequency also has to be equal to the frequency of this, right? Because you want, when this is going right, you want it to go right, and when it goes left, you want it to go left. So you basically want to match the pendulum, so that's why it should be A. And that's why B was correct if it was vertical, but god dang it, I should have read that, god dang it. Okay. Alright, 6B, hold up. Okay, this is right. Wait, this is what I did, right? What? Bro, this is really what I did and I got it wrong. Okay, hold up. Oh, okay, I see what it's saying. So it's basically just saying that this part is L squared over R over M2 is equal to L squared over R2, or R, there's R2 here. This is R1 over M1. And then you basically just get that M1 R1 is equal to M2 R2. So if you increase the mass or decrease the mass, then R has to increase. Okay, that makes sense. Whoops, that is so sad. Alright. Okay, 1, 2, 3 is correct. Alright, yeah, basically that's the logic. Okay, then C is correct. Good job. Alright, then C is correct. Cool. MG, A. Alright. C, D. Okay, that's good. What? Hold up. No, what? Seriously? I thought I knew this one. Okay. So essentially you have your M moving. So originally you have like F minus, or yeah, basically these guys could be treated as the same object. So yes, your thing is F over 2. Okay, so I got it right that it increases by a factor of 2, but why did it jump up? So mu S is less than mu K. Oh, but because it also, okay, so essentially you have F minus mg mu K over M is equal to is equal to mg mu K over M. Oh, okay, so you basically got F over M is equal to 2g mu K, right? Which basically gives you that your, acceleration is going to be g mu K, right? Because yeah. Wait. Yeah, okay. The acceleration is g mu k. Wait, that's so big brain. Okay. That makes sense. So if the acceleration is g mu k, that means like right at the point where it used to, like right at the point where the static friction stops working, the um g mu s was equal to F over M, which is your acceleration. Your g mu s was the acceleration on the top block. Oh, okay. So on the top block, the only force is friction, right? So essentially, at the point, it was the g mu s. Like at the point it was about to break is g mu s, and then it jumps to g mu k. Okay. That makes a bit more sense. I should have done this out. God dang it. Okay. So 14 wrong. Okay. All right. So A is correct for that. All right. -1. Very good. All right. Alrighty. Epic. Hey, okay, so B was correct. I remember one of my friends told me like, oh, it could be either A or B, but no, okay, so B is correct. Alright, good. I didn't troll myself. Okay, both of these are correct. Oh, what? Not even in inelastic? Seriously? Oh wow, I did not know that. Okay, hold up, what's the solution? Oh, I guess it's just heat. Alright, I see. Okay, that's right. Oh, I didn't get this one right, but I did get that one right. Easy. Epic. Bruh. Okay, so technically it's a 20, like 19 legit ones, and then like how many sillies? 4 sillies. God dang it. Okay, I gotta practice that. But let us figure out how these ones work. So consider the instant when the mass is moving vertically upward. In this instant, the mass acceleration is perfectly horizontal. Wait, what? Why? Isn't there downward gravity? Isn't this vertical, right? Okay. Oh, so when it's on the edge of its... Oh. Oh, that's so big brain, dude. What the heck? Oh, that makes sense. Wait, this is kind of funny because I'm pretty sure I guessed this. Like, I legit did it during the actual one, and I put this, and then I realized that how I did it was wrong, but I still got it right, bruh. All right, okay, that makes so much sense. Okay, why can't it have acceleration upward though? Why would that not work? Wait, why? Yeah, why is the acceleration perfectly horizontal? Why can't it like slow down? I don't get it. Okay, I guess I'll take their word for it, bruh. All right, then this one. If you have the height measured from the middle of the box, okay, that makes sense. Oh, okay, I see. So basically, you have like you have your two strings or springs, okay, and you say this is K1, this is K2. Then essentially you have K1 x1 plus K2. Do we assume that they both have length L? Yeah, okay. So plus K2 x2 is equal, or x1 because they have the same x, or yeah, we could just say or they call it d in the solution, so we'll just do that, is equal to mg, right? Then if we displace by x, then we have x over like L minus z is this theta. So essentially the force is K2z, right, times this, so K2z x L minus z, and then the force pulling the other way is K1z x over L minus z, or L plus z, right? So essentially you want to set these guys equal, or this one greater. L plus z, right? Yeah. Okay, so this is greater than, because the top one is pulling inwards, right? So we want this to be greater than that. So if we solve this, we basically get K1 L z x plus or minus K1 z squared x is greater than K2 z Lx plus K2 z squared x. And if we divide by zx, we are left with K1 L minus K1 z is greater than K2 L plus K2 z, right? And we know that z is just like mg over that, so essentially we basically get what? Mg over K1 plus K2. If we move this over, then it's just Mg on the right side is greater than K1 minus K2 times L, and then you just solve. Okay. Wait, what? Less than? Oh, I must have flipped some sign somewhere, but yeah, so this would be less than. Okay, makes sense. Alright. Very epic stuff. Alright, well that is a wrap. Thank you guys so much for watching. I hope it was helpful. Let me know what else you guys want to see. But other than that, that is all I got for you guys today, so thank you guys so much for watching again, and see you guys next time.